Hopefully you've had a moment to try this problem on your own. If not, just pause, try it, and then watch this solution video. So this is a problem practicing assigning comparative physical properties to different molecules. And I've got 4 listed here: butylamine, tetrachloromethane, cyclohexane, and propanoic acid. So for each of these to compare, it's a good idea to have a sense of their structure. So I drew their Lewis dot structures up here at the top of your screen. Hopefully you can see them. And now I'm going to compare them because I'm being asked questions like, what's the lowest boiling point, highest melting point, greatest surface tension, least viscosity? Now these are all molecules that have different general sizes, but they're all sort of the same. Chlorine molecules are pretty big and polarizable. And so while it's just this one single center atom, like those take up a lot of space. It's not a perfect size comparison at all, but I think they're close enough that we can just compare intermolecular forces, especially to practice these skills we've been developing. So my first step is to list the intermolecular forces under each one, and that each molecule would have within a sample that's pure of just it interacting with other molecules of itself. List those, and then I can have a point to compare to decide which one's going to have stronger or weaker intermolecular forces. And then that'll help me decide which physical properties will belong to which ones. So let's start with butylamine. So I've got all these carbons and carbon, 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 hydrogen bonds, and they're basically all nonpolar. But then it's bonded to this amine group, which is a nitrogen bonded to 2 hydrogens. And so here I have a dipole moment that exists here in the nitrogen around the nitrogen. So it looks like this. So this is going to have dipole-dipole interactions. I'm also noticing that it has these NH bonds right here that can participate in hydrogen bonding interactions. So if I'm going to list the intermolecular forces that exist for butylamine, I'm going to use abbreviations here where LD is going to equal London dispersion. DD is going to equal dipole-dipole. And HB is going to equal hydrogen bonding. So looking for butyl amine, I know it's going to have London dispersion forces because it has electrons, and that's all I'm really looking for to assess that. It's going to have a dipole-dipole interaction because it has a dipole moment, and it has these 2 NH bonds in the molecule, so it can have hydrogen bonding interactions. All right, next I'm looking at tetrachloromethane. So this has little dipole moments between the carbon and the chlorine, depending on the electronegativity table you look at. But they're all the same bonds equally spaced apart. So this is overall non-polar. And so because of that, it's not going to have that dipole-dipole interaction. I also don't see any NH, OH, or FH bonds in this, so it doesn't have hydrogen bonding. So it's just going to have London dispersion forces. Next, we have cyclohexane, C6H12, all carbon-carbon and carbon-hydrogen bonds, and those are always non-polar. Write this over here. And so that means that this will also just have London dispersion forces, no dipole-dipole interactions, and no oxygen-hydrogen, nitrogen-hydrogen, or fluorine-hydrogen bonds to make a hydrogen bonding interaction. So just that. Then we have propanoic acid. So here's another one that has a dipole moment right here. And also I see oxygen-hydrogen bond as well. Now remember, our oxygen-hydrogen bonds are stronger than our nitrogen-hydrogen bonds, but at the same time, the other one has 2, So this one has London dispersion forces, dipole-dipole interactions, and it has hydrogen bonding. I can also note in looking at my butylamine versus my propanoic acid that my propanoic acid has another oxygen with lone pairs that can participate in hydrogen bonds with the OH bonds of other molecules. And there's only one lone pair on the butylamine, but I'm also noticing that the butylamine is a larger molecule. Actually, it's about the same size. The oxygen's going to take up a lot of space, just like the carbon, about the same. So looking at these, I would probably decide this based on the strength of the dipole moment and the strength of the hydrogen bonds. Now, the oxygen-hydrogen bond has a greater electronegativity difference. So I think we can state that the propanoic acid has a stronger dipole-dipole interaction, especially because it has two oxygen atoms that are pulling electron density away from the other molecule. So I think that my propanoic acid, let me redo that. My propanoic acid is going to kind of win the comparison for strongest dipole-dipole interactions. For All right, so the dipole-dipole will be stronger for propanoic acid. And then if we think about the hydrogen bonding, what we saw in our previous example was that the number of hydrogen bonds is really meaningful. But when we're looking at our nitrogen with our 2 and our 1 lone pair versus our oxygen with 2 lone pairs and 1 hydrogen, they're going to be somewhat similar. I think that the oxygen-hydrogen hydrogen bond strength being stronger than the nitrogen will tip the scales in the favor of propanoic acid. So if I was just going to sit here and guess between the two, I would think that the propanoic acid would have stronger hydrogen bonds. Sorry. In terms of London dispersion forces, I think they're going to be pretty similar. There's basically a 4 atom backbone with a 5th. I think the surface area of the butyl amine, though, is larger because it's all in one row rather than having a branch. So I'll give butyl amine a slight advantage on my London dispersion forces. And what I'm doing here is I'm comparing to try to figure out which of these is going to have the strongest intermolecular forces, because that's going to dictate how I answer a lot of these questions down here. So I'm going to go out on a limb and I'm going to say that I'm going to make a choice. I'm going to say propanoic acid is the strongest. And then butylamine is the next strongest. So I'm going to actually, so we'll do this one. Second strongest. How about that? Now looking at tetrachloromethane and cyclohexane, I kind of have to figure out between these two. They're both London dispersion forces, right? So which ones are going to be stronger? The cyclohexane has a lot more atoms. It's heavier, or not heavier, sorry. It's got a lot more atoms, has a lot more connections there, more atoms, but the chlorine atoms are going to be larger than the carbon atoms. So weighing that, it's like which one is larger, which one is smaller. And so I think that the cyclohexane is going to be a larger molecule and therefore have the larger London dispersion forces. And so I think that the weakest one is actually going to be this tetrachloromethane. So we kind of go from strongest to weakest. So I'm going to say that, so I'll write this out down here at the bottom, that my propanoic acid is going to have stronger intermolecular forces than my butyl amine, which will have stronger forces than my cyclohexane, which will have stronger forces than my tetrachloromethane. Do this. Or actually, let's reverse that. If I wanted to, I could go and kind of compare boiling points. It's not going to be a perfect comparison because the size of the atom or like the mass of it is going to affect the boiling point as well. Sometimes it's a helpful metric. It is not going to be a direct way to compare intermolecular forces, though. If I do that, I find that my propanoic acid has a boiling point of 141 degrees Celsius. My butyl amine has a boiling point of 79 degrees Celsius. So that supports our decision that the propanoic acid has a stronger intermolecular forces. Now, there might be other things going on there too, but that's a pretty big difference. And so I think it's safe to say that the propanoic acid has a stronger set of intermolecular forces than our butyl amine. If I continue down this path, I actually find that the butylamine, tetrachloromethane, and the cyclohexane all have really similar boiling points. And so that might be a little bit harder to kind of like tease apart which one is stronger. So I'll go with what we actually decided for our order based on intermolecular forces to answer these questions. But they're all between about 76 and 80 degrees Celsius. So the Cyclohexane is about 80 degrees, and the tetrachloromethane is about 76 degrees. So I think that this calls into question a little bit let's pull this up. Especially the cyclohexane and the butyl amine, which one is stronger there? Um, However, I'm going to keep our order based on the intermolecular forces and the hydrogen bonding, because those hydrogen bonds are going to play a role in how things like surface tension and viscosity play out. So this has been a lot of work. We haven't even answered these questions yet. But now that we've done all of this, it'll be quick to go through these because we really need to know strongest versus weakest to answer these. So when we look at A and we say which one will have the lowest boiling point, for this one, we're really asking what has the lowest IMFs. And so that we've decided is our tetrachloromethane. So our answer here is going to be CCl4. Now, the highest melting point, this is going to be high intermolecular forces, because our melting point and boiling point increase with intermolecular forces. So for this one, we're going to go with our propanoic acid. Now, the greatest surface tension increases with intermolecular forces. So again, we're going to want to have high intermolecular forces. So it's going to be our propanoic acid. Least viscosity. So that means it's going to move fast, not slow. So we're going to look for low intermolecular forces, which means our tetrachloromethane will probably be our least viscous of these molecules. Now, these next two are coming back to this idea of like dissolves like. So which molecule will dissolve in water? And water is going to be polar. And it's going to have hydrogen bonding, and it's going to have dipole-dipole interactions and London dispersion forces. So I'm looking at these molecules and saying which of these will dissolve in water, which will have London dispersion, dipole-dipole, and hydrogen bonding. And that's my butylamine and my propanoic acid. So for this one, it's going to be both. And then for the next one, which of these will dissolve in hexane? Hexane is just a nonpolar molecule, so it'll just have London dispersion forces. So the molecules with only London dispersion forces, no dipole-dipole, no hydrogen bonding, will be the ones that dissolve in it. And so I've got two for this one as well. I've got our cyclohexane, and I have our tetrachloromethane.